memory configuration. So if you look at line number 5 and 6, this is
Hmm.
exactly what you defined in the memory command.
Right. Yes.
And
And also the
then it will
attributes.
start looking at each of the sections and start recording each of the sections.
Right.
And
And
it will,
I should mention that
yes,
these are the relocatable object files that it had created. And
yes,
it is all right. So we are going to focus on the linker today, and try and learn about memory layout of an application, basic syntax of the linker script, essentially the LD files, then what a map file is and what information it gives us, input and output section of the linker script, and then defining our own section again in the linker script, and then exporting some symbols from the linker script and why we would want to do that. Okay, did I miss anything, Rajat?
no, I guess you
Okay.
covered it very well. The only thing I would like to add is whenever we talk about linker, right, and there's a common myth where
Mm-hmm.
people say that I don't care about linker because when I write the applications on C, on desktop, using my
Mm-hmm.
C, I never use linker. I don't fiddle around these things. So
Mm-hmm.
this is a very embedded specific thing.
Yes.
But actually, that's not true. And
Yeah.
that's where people misunderstand it. Just because you didn't call linker doesn't mean linker didn't get called. There's a
Yes.
default linker that gets used
Linker script.
behind the before yeah, there's a default linker script that comes with your compiler, and
Mm-hmm.
the compiler can make these assumptions because there is an operating system over there.
Right. 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 So
So
GCC
operating
in
system is
uh
always going to map them into the same virtual sections.
exactly right. So GCC first of internally, calls assembler and
Yeah.
linker is fed with a uh, default linker file. Maybe we'll also
Yes.
take a look at that. I was just looking at the command using which this gets printed, so we can also show that what's the
Okay.
default script it uses.
And the same thing goes for startup as well.
Oh yeah, yeah, yes,
That-
yes. There is a startup file, and
yeah.
oh, that reminds me. So most of the people think that main is the
Is the
entry
first.
function. Yeah, and this may be true for apps that are written on operating system, but this need not be true for embedded.
Yeah.
And even actually, for operating systems, it's not true. It's just that there is a startup file which gets called first, and in that there is a reference to main,
Yeah.
and hence people are required, or programmers are required to write main again on an
Yes.
operating system. Cool. So did we miss anything again in terms of
Yeah,
topics?
so that's
Hmm.
so I think it is this abstraction that that the compilers based on operating system provide, that
Mm-hmm.
a lot of people during their time don't understand what a .text section, .data section, .bss sections are, that
Hmm.
we'll cover now,
Yes.
and what is the importance of these sections
Yes. With respect to a program. Yeah.
with respect and most of the section that they actually fiddle around, most of the section that will sound very familiar to them are stack and heap.
Yes.
Yes, and not these first three sections because they are very
Yes.
static in nature.
Yes. Makes sense. Yeah.
Yeah,
Cool. Okay. So let's maybe then, move on to the build process
yeah,
and go from there. So let me maybe explain this part.
yes,
Okay. Perfect. So what we are wanting to first, clear our heads with is that, we typically write some C code, and here and there, if required, some assembly code, right? And this assembly code specifically, uh, depending on what the extension is, means different thing. So for example, there can be dot, uppercase s, or there can be dot lowercase s, and this becomes important, okay, as we'll see. So let's do this then. So usually we'll have some header files, some .s files, and some C files, and all of this here, this much, this we usually refer to as the compiler, usually. but it's actually a build process in itself, and the standard term for all of these subcomponents, which we'll discuss, is called the toolchain. Right? So, right, and this compiler here usually is GCC. So when we call GCC internally calls the preprocessor. After that, it runs through the compilation process. Then assembler gets called, and then linker gets called. Now let's maybe briefly go over each step. So let me clear all of these. All right. So we have some files that we feed to GCC. So what GCC will do is call the preprocessor, and preprocessor will deal with things like hash include, whatever header files and all of that, the macros, text substitution, all of that this will take care of, and it will create some intermediate files with the .i extension. That is not seen by us usually. There are commands in which you can stop GCC after the preprocessor stage, but let's not go there right now. So there are like intermediate files, which are the I files, and then after that the compiler gets called, and the compiler will then convert this C syntax to essentially ASM or assembly. Right. So at this point, you have the .s files, lowercase s. Now, the other thing I should mention is we also input assembly files here, and these are the assembly files with the uppercase s as extension. And what that means is that this preprocessor should be run on these files. So, within the assembly file itself, you can also have hash include and so on and so forth, few of the assembler macros, GCC macros. So the preprocessor will also process those. If you have a lowercase s assembly file, then that will be fed directly to the assembler. During the assembler stage, it doesn't get preprocessed. Right? It's a whatever. It's a minute detail. So lowercase and uppercase s means that uppercase file will go through preprocessor, lowercase file will not. Okay, so all the assembly files that are generated here and the assembly files externally provided with lowercase s will be fed to the assembler, and assembler will generate something called relocatable object code.
Files.
Yeah, object file. Yes, object files. And their extension is .o. And in these files, there are like machine code, but they will the addresses for certain function calls will not be substituted. Function calls or symbols.
Yes.
They'll be retained as is. And the reason to that is sometimes you may have, let's say 1.0, where there is like a function call to 2.0. Like some function is defined here that's getting called here. So assembler will not resolve those addresses. It will just keep the symbol here. And later on, these object files are kind of all fed into the linker. And the linker is the one which will resolve these addresses and substitute the right number here. And also it will merge these different object codes into one final file, typically, right? And that will be your ELF or executable linkable file format. Right? ELF is executable linkable file, and here all the code exists with all the addresses resolved, all the symbols, all the symbols they're being replaced by the actual relative or absolute address as a number. And this exe, the .elf file, this can be fed into some sort of a tool. We'll talk about that tool later, and that can then be flashed on your controller, the memory.
Yeah.
Right. And sometimes what people do is use some other tool in between and convert this to a .bin file. And that .bin file has zeros and ones straight. In the ELF
Yes.
file, you tend to have like some header, some information, then code, some more information, blah, blah, blah.
Yeah.
So the binary file is like the stripped version, just zeros and ones.
Yes.
Okay, did I miss anything in this journey?
No, I think you covered majority of the things. The only thing I would like to highlight is that this is not only limited to GCC. This is how the compilation flow on. This is the C standard compilation flow. which majority of the C compilers follow. And you can use Clang, etc., and the steps still remain the same. The formats of the files may be a bit different. The format of the intermediate files, not the final files, the format of the intermediate files might be different, but more or less they all follow the same process. And even if you take out C compilers, if you look at this build process flow, the only portion is preprocessor, which is very specific to C standard.
Right.
Even if you go to other compilable languages which are compilable, more or less they follow the same build process. They may not have the assembly files. They might have, for example, Rust might have .rs files, but more or less the steps still remain the same. It goes via compiler generates intermediate representations. Those intermediate representations that convert into assembly, then optimizations are done, and then it is passed to linker for its placement, etc.
Right. Perfect. Okay, so then what we can do is move on from here to talking about the memory layout. Okay, do you want to speak to this?
Yeah, so understanding memory layout is very critical before we jump into linker. As I said, the reason for this is because a lot of people who come from C background and are very new to embed, even a lot of people who are in embed who have never fiddled around with linker, don't understand what is the difference between a .text, .data, and .bss section. As per most of the people, most of the time they are only worried about stack and heaps because these are the dynamically manipulated memory sections.
Right. And these are like more visible to the programmer.
More visible to the because these cause debug problems, right?
Yeah. Most of the debugs involve this.
So stack people are majorly aware because whenever something crash happens, everybody asks them, can you backtrace it or give me your stack frame?
Stack dump.
And heap mostly comes into picture because heap is the reason of that problem somehow.
Yeah. There's always some segmentation fault, some heap overflow, exhaustion of the heaps.
These are much common known sections, while the other sections are not very much known. And it is crucial to understand what these sections are before we jump into linker and see how linker manipulates these sections.
Right. It's very crucial to be able to appreciate what linker does.
Yes.
Go ahead.
Additionally, I would like to highlight, we may not be able to cover it in that detail, but Dave has already covered it in a lot of details in one of his videos. We may link that video. He gives live examples of it. Yeah. So what does these sections actually mean? So .text section, before we jump into what goes where, a small description. .text section is basically code. Your exactly instructions that your CPU has to process.
Right.
And when we talk about the .data section, the .data section is something which is initialized. Something which is global or static and is initialized.
Right. This could be global
or static.
Right. Or static.
Yeah. Right. So anything that is initialized, not constants. Constants have their own section, but let's not talk about them right now. And uninitialized data is anything that is global or static and is not initialized. That is BSS, .bss segment.
Right.
And why do we talk about only global and static?
Right.
So this is a crucial thing. So anything that is not global or static goes into what's called a stack frame. And I guess if we go a bit back, we covered the concept of stack frames. Yeah, maybe we can go up a couple of slides back.
Couple of slides back, okay.
I guess we may need to go up a bit.
More up?
Yeah, more up.
Yay! Whee!
Yes.
Okay. Oh, yeah, okay.
So we covered the concept of stack frames over here. Yeah. So when we talk about, whenever a function is created or whenever a function comes into execution, it creates a stack frame over to the stack. Right. And what this stack frame contains is all the local variables that are initiated, and local variables, whether it is initialized or uninitialized, a frame pointer, and return address, blah, 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 blah. But the main thing is all the variables that are within a function scope goes into the stack pointer and not in the stack frames and not on these dot data and dot BSS sections.
Right. Right. Makes sense.
Yeah. And and all this data is encoded within the instructions itself.
Yes.
So you will have a push stack value of A, push stack value of B being done in the instructions itself, and not a separate place where only value of A or B is there, which is the case of dot data section.
Right. And I think, we can come to that during the demo. We can actually show the LST file or disassembly.
Yes.
And go from there. Okay, moving on back to, not sure which slide. Where were we?
We scrolled a lot.
Oh, okay. Getting ahead of ourselves here. Oh, all right. Someday we'll be there. Here.
Yeah.
The colorful slide. Yeah.
Okay. So as we discussed, if you look at the example on the left, the first integer declaration, which is on line number 5, we declare int global data and we initialize it to 10. And this since it is a initialized data, it will go into the dot data section.
Yes. I think, one other way to think about it is that this 10 needs to be stored somewhere.
Yes.
And that somewhere is the dot data section.
Yes.
All right. And kind of anything that will be initialized, that number needs to go to, anything that is global or static, which is initialized, that number needs to be saved somewhere in permanent memory, kind of as an initialization value, and dot data section is the place. Okay, go ahead.
Yeah. Okay. So, and similarly, when we talk about a stack var, the stack var will actually be located in stack.
Yes.
Because it's a local variable, since the main scope has started.
Right. And
when we talk about heap var, the variable that is declared, the variable that the memory that is allocated by the malloc, the 4 bytes that the malloc is gonna allocate here will go to heap, but the pointer that is gonna point to that memory will go to stack because it's a local variable.
Right.
So heap will have heap var that will point it to a memory within the heap.
Right. And when
so 7 so 7 here will actually reside on heap, but heap var will be in stack.
Right. And then it is actually holding an address of this guy.
Yeah.
So address itself lives on the stack, but the content of the address lives in the heap. That is the idea. And let me also.
And the reason and the interesting reason to do that, the whole concept of stack is so that when the function goes when the function comes in scope, its stack frames come in scope. When the function goes out of scope, its stack frame goes out of scope. Also that means you cannot access stack variable, heap variable, they don't exist. So that's why these go into the stack, because you want to have the concept of scope tied to them. Which you cannot do with the global data, right? Global data should be accessible to everyone. So you want it to be in a memory that doesn't go out of scope ever.
Right. Talking about scopes of the global, there can also be static globals, and their scope is kind of limited from the standpoint that the compiler enforces it. But if somebody has their address, they can still kind of reach out from another file and mess up the value.
Yeah. So I guess what I need to change in the definition is not the scope, the lifetime of a variable.
Lifetime. Yeah, fair.
So wherever you want a lifetime that should not be tied to a function should go into a dot data section. When you want to tie the lifetime of a variable to a function, you put it in stack.
Fair point. Yeah. Okay, so I think we talked about these, and then here we are just printing them. So
these are basically instructions, right? So all of this will get compiled, transformed into instructions, and will be given to the dot text section.
Right. So they will live here in the dot text section. Right. Okay. And then the free here is a function call again, which just frees the heap memory. So that's just for writing accurate program. and
Yes.
that's about it. So we talked about data section, the BSS section. Oh, I suppose we did not talk about the BSS
Yeah.
section. We did not talk
So
about this.
BSS section is anything uninitialized, but it still has a lifetime.
Hmm.
So a lot of people, and this is where I say a lot of people just say if anything has not been initialized, it initializes to zero.
Zero.
Well,
Yeah.
actually, that's not
Myth.
true.
Yeah,
That's a
it's a
myth.
myth.
That is because of some standards that dictate that the BSS section should be initialized to zero. And this is
Hmm.
what happens in the startup file, which is not visible to them.
Right. So in the startup file,
Yes.
this region gets initialized to some value. Usually
Yes.
that value is zero, but it
Yes.
need not be.
It need
In
not
certain
be.
cases, it can be set
It
to
can be
F.
one.
Yeah, it can be all ones. And in such cases, if you have written your code assuming that this value by default will be zero, yeah, you are in for a surprise. Right.
Yes.
So just be
And
mindful that if you do not declare or define a value for a variable, doesn't mean it will be zero.
yes. And
Yeah.
whenever we talk about a binary, right, what a
Hmm.
binary contains. So a
Hmm.
binary actually is a combination of dot text section,
Hmm.
dot data section,
Right.
and that's all.
Yeah. And the BSS section is left out. Right. But
Because
there is something interesting. Yeah.
there's no meaningful information over there. So
Yeah.
what
Yeah.
we do is we just take the start address and the size of the BSS section and initialize it during the startup itself.
Startup. Yes. So the start of this region, right,
Yeah,
and the size is what we are interested in, and we can skip saving this makes no sense. We just need these two
exactly.
information so that the startup code can on the fly zero out or initialize that memory to some value.
Yeah.
Oh,
And the reason
perfect. Mm-hmm.
and the reason you should never, assume the value of zero is because I've seen a lot of customers, I've seen a lot of people who wants
Mm-hmm.
to save this startup time, which goes into initializing BSS to zero,
Yeah.
and
And
just completely skip it
yeah.
and be like, in our code we never make an assumption that uninitialized variables are not zero.
Hmm. Hmm. Right. They
So
take the responsibility of not
they take
screwing
the
it up.
responsibility of assuming that uninitialized means it can have any value. So
Right. Right.
yeah,
I mean, they are aware of what they're, doing. So
yeah,
I think that is fair also. And I suppose that is where, C makes like one of the places where C makes it easy to shoot in the foot.
yeah.
So that's that.
And so
Mm-hmm.
this is where it goes, and just pushing a bit
Hmm.
of the hardware details on the people.
Sure.
So whenever we initialize, and the reason you should not make this assumption is if you're on a MCU, this section actually relies on RAM, right? SRAM.
Hmm. Hmm.
And when you
Right.
power on the SRAM, people assume that since I am doing power on, SRAM will be all zero, but that is
And
actually
it's
not
not.
true.
Yeah, it's not.
SRAM by its electrical characteristics can
Can
have
have
either
random.
strong ones or strong zeros. So
Fair.
and that is
Fair.
randomly distributed.
Right.
So when SRAM gets initialized, it is in a very random variable state.
Yeah. Yeah.
And actually, this is
Mm-hmm.
used in the industry. This characteristic of SRAM is used
Hmm.
in the
Hmm.
industry to
Hmm.
make something called puffs, physically
Right.
unclonable functions,
Functions. Yes. Yes. Yes.
because it is
Right.
completely random. So it becomes a unique identity for a unique device.
Device. Yes. Well, okay, let's not go in puff, but I think I
Yes.
have a question on that I'll ask you later.
Yeah.
Cool. Okay, let's talk about the linker in a little bit more details. So essentially, what's happening is we talked in like the earlier slide that the linker is getting the .o files, which is the relocatable object, and then I am showing here the .a file, and .a file essentially are archives. Right? And
Yes.
archive files are essentially a zip version, so to speak, of many O files. So within that, it's like a collection of O files. So essentially all object files here, right? Many within this. So what happens is object files are fed to the linker, and the linker will try and resolve references in each object or library file. right? So internally within the file itself, there will be references to the code, and it will try to resolve that per file. Right? And what it does then is it will have after the resolution within the file itself of the addresses, what it will do is it will update those object files, and now it will operate on those. And let me just clear this out just so that there is more space. Okay, so once these object files are updated with the resolved addresses, what it will do is it will assign the data and code individually the addresses at this point, right? Sorry, I think I made a mistake. Yeah, okay, sorry. Here it is resolving the references, and at this point what it is doing is the instructions, they are getting the addresses, right? Each one of them local to the
So
file.
each
You
of
want
the
to
blocks, each of the relocatable block are getting assigned some addresses.
right. So each file then, internally the instructions get addresses, and then within that, if there were some symbols, then those also get the addresses. All right. Once address allocation is done at the file level, then the next step is that it now needs to find or kind of resolve the parts where it could not find the address. So for example, if there was some function here, right, that was being called from here, at a file level, it would not be able to resolve that because this symbol doesn't exist in the same file, so it cannot resolve that. And in this stage, what it is doing is it is linking or saying that this symbol exists in another file. So it's doing that kind of a resolution, right? And now it has like a rough map as to who is where. And then the final stage, and these two kind of are like mixed stage, but I have separated them. So what happens is in this final stage, it is going to, well, not really final stage, second to last stage. What it will do is it will take the linker file, right? And using the linker file, it is now going to take different sections from these files, right? Each one of them would have had its own data section and some text section. So it will take all of these text section from all the files and then merge them together to create one final file here at this point, where all the text section is available, where all the data section is available, some debug information, and all the addresses are like already resolved at this point. So it has just merged all the code together in like a single file. And then at this stage, what it will do is within the linker script, if there were some instructions, right, to generate certain symbols. For example, we talked about here at this point that the start of the BSS section and the size of the BSS section is all that we care about. Then this start of the BSS section will need to be exported as a symbol. And that
Yes.
is kind of, added in this stage. And so the final ELF that we have, it will have the text section, the other whatever data section, and some symbols,
Yes.
which is having which is representing the address of the BSS section, and some size or end address of the BSS section, some debug information. So all of that is available packed in the ELF. So that is kind of the journey of the .o files towards becoming the ELF. Did I miss
Yeah.
anything, Prajit? You think I
No, I
skipped
guess you
on
covered
something?
it. Yeah.
Right.
No, I guess you covered it.
Okay, perfect. So now what we can do is maybe let's talk
Jump
about the
into code.
syntax. Yes, okay, let's jump into code. For that, let me just see if I have, just give me one moment. Let me get my tools in place so that we can scribble on the screen. And without controls. Okay, let me know if you can see. Okay, you cannot see definitely because okay, so I think we'll have some issue. Let me so let me do this. Let me stop presenting my screen and then I will reshare my screen. This is going to be fun now. This is the part
Just
where
hope it gets recorded this time.
yeah, Yeah. Well, for our audience, this is the second time we are recording the same topic because the previous time things did not go as planned. We talked for an hour and then figured that the recording is not available. So yeah, that happens. Okay, Rajat, let me know if you can see my screen. Can you?
It's coming up. Yes, I can see restart code fix.
Nice. Okay. And then also, can you see? Oh, well, you can see smileys. Okay. Let me go and start screen annotation. Stop screen annotation. Annotate without control. Nice. You can see the red ink on the screen.
Yes.
Nice. All right. Let's do this. Where do we want to start off from?
We want to go into the linker script and let's. Okay, let's.
Oh,
I think we should give a first give a
overview of
overview
what
of
is
the
what. Right.
of what is what.
Okay.
So it's
Yes.
a very simple program that we have wrote to just showcase what linker does, and all this program contains is three source files, and we will only look at two. We will not jump into startup.c.
Yeah,
We'll have a
this
look
we
at
are skipping.
startup.c later.
Mm-hmm.
So the first file is add.c, which is nothing but it contains our add function that takes two variables, add them and return them.
Right.
And then the second source file just calls this function.
Yeah.
As
so
simple as that.
Right. So the second source file is the main.c, which is here. And it's just calling that function. There is a header file here. And we have some globals, initialized, uninitialized. Again, so that our audience can follow us, these will go into the .data section. This will go in the BSS. These parameters, when function invocation goes on stack, which will come to later. Yeah. Okay. And
so
then
the aim of this whole activity is to showcase that whatever we said is actually happens, and we will actually look into all of that.
Yes.
Yes.
And then we have the linker script.
Linker file.
Yes.
Linker script.
Yes.
And
Perfect.
then we have a cmake list.txt. You guys don't have to worry about it. It's just the build system for us.
Correct. So this kind of, just automates.
Just automates the build process.
Yeah, the build process for us. And we did not want to kind of, spend time on showing build commands. Okay. So let's go to do we want to talk about the linker script?
Yeah, let's first talk about the linker script. Let's first talk about the basic syntax of the linker script, right?
All right. Let's do it. Yeah. Okay, so maybe I'll just introduce and you can take over. So the linker script can have like any name. Its extension usually is .ld. That's all. And
not mandated.
Not mandated. This can
not
also
mandated,
be like
but yeah, but it's
.txt. It can be anything. It's just that you pass it to the linker using the -t option.
T option.
Right. And maybe when we compile, we can show the compile commands.
Exactly.
Yeah. Okay. Perfect. Now you take over. Let's do this.
Okay. So the two major portions. So there are two major sections in the linker that the user has to write. The first segment that is usually called is the memory segment. So so why do we use memory segment? The memory segment is used to give linker the highlights of all the memories that you have. Not have all the memories you want linker to be aware of. All the memories you think linker should be aware of should be highlighted in the memory segment. And so before I go over here, so there's a myth that people usually consider there are two sections, ROM and RAM.
Oh yeah,
that's not actually true. It has been a legacy terminology. People have been keeping using it, but you are free to keep them whatever name you want.
Correct.
But people like to keep the name of ROM and RAM as other people are familiar with it.
Right. So maybe let me put this more formally. So memory here formally is called a linker command.
Yes.
Right? And each command kind of has a curly brace opening and closing. Similarly here section is a command and it has a opening and at the bottom there is like a closing brace.
Yeah.
Right. Go ahead.
Yeah. So
and by the way,
in the
I wanted to mention that memory and sections these are standard keywords for the linker script. These
Yes.
are part of the linker script. Has to be all caps.
GNU
I
linker
have not.
script.
Fair. Okay. Yeah, that's also correct. GNU linker script. This needs to be all caps. And by GNU linker scripts, we mean whatever ships with GCC,
GCC.
right? As part
So
of that toolchain.
this may change for IAR and Kyle, but the overall concept how the linker works doesn't change.
Correct.
You still need to mention it in the same way, just keywords changes.
Yeah. And kind of there is usually a documentation for that toolchain's linker. Yeah,
yes.
Yeah.
And the amazing part with the linkers is that you don't have to fiddle around them with much. You have to fiddle them around at the start of the project.
Yeah.
And there are very specific scenarios, like 1 in 100 time when you have to go back and touch them.
Yes.
And that's why you hire one guy who know all these dark secrets and rest 90 guys who don't know about it and don't care about it.
Yeah. And then that one guy is like worshipped also because he knows the black magic. In our case, all 5 of us know the black magic. Okay, moving on.
Yeah. Okay. So in the how do we define a memory portion or memory to the linker? Is we start with the name. We give that section that memory segment a name. Now now this name has to be, you have to use the same name across the linker once you define it, because whatever you define over here will be used in sections.
Right.
To command linker where to put things, which section to put in which memory. So we start off with the name, and then we have something called access permissions. So these access permissions are not hardware access permissions. These are like access permissions that linker should respect while doing all the linking. So let's say while linking, it sees that a code in another section is trying to do there's a code that you are putting in flash segment which is actually doing write accesses. So it will give you a warning at that time itself that this memory segment should not have any write accesses. It is only readable and executable.
Correct. So the idea is that you have something somewhere in some memory, could be within this or could be here also, which is attempting writes in this memory region.
Yes.
And because the attributes are set here to read and execute only, the linker will figure out that this write is not allowed in code, and it will give some linking error.
Yes.
Yeah. Also, I should mention that there are like other attributes also. So for example, R is read, W is write, X is execute, A is allocatable, and then there are some things like I and others that I
there are
never
multiples.
used. Yeah. So, okay.
So
cool.
Moving on. So you give a memory, you give its access permission. Now, how do we typically define a memory? We define a memory by its start address and its size. So to define the start address of a memory to the link to the GNU linker, you have to use the tag origin, and to define the size, you have to use the tag length.
Right.
So your end address of the memory becomes 808.0.0.0.0.0 plus 100.0.0.0. Now, some linkers have a different methodology. So instead of doing origin and length, what they do is origin and start address and end address.
Okay, so this can be start address, and then separately this can be end address.
Okay. So rather than talking about start address and size, they talk about ranges of memory address.
Right. Starts here, ends here. Yeah.
Ends here.
Okay. Also, I should let me just add this. Then this colon is mandatory. Right?
Yes.
These colons are mandatory. This separates the name and attributes from the description of origin and length. Again, all caps for GNU linker scripts, and there has to be a comma here.
Yes.
Right. And equal to signs to assign the values. Right.
Yes.
Okay. One more thing, which is this number here can also be in decimals.
Yes.
And you can also use units. So, for example, 4K, 5 MB, all of these are valid. Yeah, the usual sizes of sizes related units.
Yeah. So, how do you get these addresses? We'll look into future. We'll actually play across a device, and we'll look into how to get these addresses. And
Right.
I guess we did a podcast as well on getting
Yeah.
started. The blinking
Reading the
LED, how to
data.
get
Yeah.
started, reading the data
Reading the
sheet,
data
how
sheet.
you get
Yeah.
these data, how do you get these numbers as well.
Yes.
So we'll again look into all of those.
Hmm.
Uh, but the second important thing is defining the sections command.
Hmm.
So whenever we talk about sections, the common syntax is a output section, colon, braces,
Mm-hmm.
the input section redirected to a memory segment. This is
Right.
the syntax of a sections command.
Right. So this is the output section, and this is the memory.
Your memory segment.
Right. And then these are like the rules for merging.
Rules of the input section.
Right.
Rules plus
Yeah.
input
Okay.
section.
Yes. Rules for merging the input section.
Yes.
Okay. Perfect. Let's move on. Yeah.
Yeah. So when we talk about layers, so let's take an example. So here what we are defining is that we are defining an output section called dot vector,
Mm-hmm.
which I think we ate a brace. We ate up a brace.
Oh, okay. Yeah. Okay. Yes. Sorry. What's happening is, my function key, which brings over the annotation tool, is also the smiley related
Emoji.
key. Yeah, emoji. Okay, let's
Okay.
move
So
on.
yeah. So the vector. So here we are defining an output section called dot vector,
Mm-hmm.
and this output section, how linker should generate this output section is it should first align the memory, and the dot is a very specific meaning in the linker script. This is called a
Yes.
position counter or location counter,
Right.
which is basically the address the you are at specific point.
Right. Right. And this typically would mean that you start off with this, memories starting point, and then
Yes.
based on, as you assign it, it will increment further. Right. So
Yes.
if you have your memory here, and let's say for whatever reason your memory started at the number 3, for example. So when you're aligning it by 4, this location counter moves to 4 because that's the next
Yes.
aligned address, and it will start to fill content from here. It meaning the linker.
Yes.
So the linker will put here the value of dot as 4. Okay, go ahead.
Yeah.
Go ahead, Rajat.
So
Otherwise, I'll distract.
in the second statement,
Yeah.
we actually declare a symbol called underscore s
Yes.
vector, and we assign
Right.
it the value of the dot.
Yes.
And we do
Yes.
it point to time to time. This is actually useful in debugging because all these symbols get recorded in something called a map file, and you can always look at the map file to understand where it all started by looking at these symbols,
Right.
looking at the
And
addresses assigned to these symbols.
right. And so this S vector essentially means start of the vector region, which will point to, 4. And
4.
then let's say this vector is like vector region is like maybe 10, 20 bytes. And then towards the end here, we have the E vector, which will point to that end of the
Yeah.
vector region. Right. And
Yeah.
both of these will be exported as symbols in the symbol table.
Yeah.
Okay. Okay.
The second statement says that you should include all the sections named dot vector and all the sections named dot reset handler. And then whatever you are left with, align it again with four bytes
Right.
and record that value in end vector and place all of this into the flash segment.
Correct. So we
Now
have.
I would like yes. Okay.
Okay, I'll just point out one more thing. So what we are saying is take all the O files, and within
Yes.
that O files, look for the dot. Okay, keep working. Yes, look for the dot vector section and dot reset handler section, and then put all of them here, right?
Yes.
And this is where you have the S vector, and this is where you have the
E vector.
E vector, right? And one more thing is this syntax here, the star brackets dot vector This is vectors, TORS, yes. So this is essentially what is telling to look for this section in all the object files.
Yes.
Right? This is a wildcard symbol.
Yes.
Right? So we look for essentially all vectors section, all reset handlers section, put them at these address, and this section will be called dot vector, which is
Yes.
the output section as mentioned here. Yeah. Okay. Go ahead, Rajat.
Yeah. So the reason of putting a keep over there is,
Mhm.
so if you look at line number 23 and 24, they start with the keep keyword. So the keep keyword tells the linker to keep the section irrespective of whether that section is used or not.
Yes.
So for example, if you have a code piece in vectors, and if linker doesn't find any of the code interacting with this section,
right,
and if you have selected any kind of optimizations in linker like remove unused sections, etc., it will just
right,
remove this vector section.
right,
So this keep keywords direct the linker that even if it is not used, just keep it.
right. Don't optimize it out. Don't throw it
Don't
away.
optimize it. So it's like the volatile of linker, maybe.
Yes.
Maybe not a
And
very exact analogy, but
the
yeah.
analog, yeah, sure. And you
So-
know, the use of this becomes a lot more clearer once you understand how the M class controllers, boot and work. Right? Nobody is making a reference
Actually
to.
they know, right? We already
Oh yeah,
covered
because
it.
we recorded that first. Yeah, sorry.
Yes.
My apologies. Yeah. Okay.
Yeah.
Perfect. All
So-
mixed up. Okay.
Yeah.
Go ahead.
So I guess we let's compile the code and let's show them that what we said actually works.
Okay, let's do that. So let me
Yeah.
bring up a terminal at the bottom here. What was the command again? I think it was
CMake
Should I be
space-
going to the experiments directory? I think
Yes. Experiments directory CMake
CMake minus
hyphen capital B
capital B, yes,
/build.
// and build.
No space between / and build. We want to create
okay.
build
That's
directory.
the directory. Yes, and then I think there was minus
hyphen
S.
capital S
Okay.
space /.
Okay. So the source is the current. Source is the current directory, and the build content should go in the .build directory. Okay. Perfect.
Yes.
Hope and pray that it works. Yes, it did.
Yes.
So
we can go into CD build.
yes,
and we
then
can
do
just
make.
run make.
And it did not work because I messed
okay.
up the syntax.
Syntax.
Somewhere I messed up the syntax, and that is okay. Which line? Which line have I missed?
Okay.
Line number 21. Why?
Does it not like the brace you put over there? You deleted the original brace.
Well, it should like it. There is nothing to not like. Okay, live debug. Syntax error. Can I cheat here? I'm wondering if I just threw in some hidden
Just
character.
look if there is something after the colon.
Yeah, I replaced it now.
Okay.
I just copy pasted and replaced. Interesting.
Yeah.
There was a hidden character.
Yes.
Okay. It doesn't show
Maybe
the
a
commands.
emoji.
Very much possible. Yeah, very much possible.
Maybe while opening that menu, you misclick the mouse, which VS Code is not able to present.
Yeah, that is very much possible. And given that it's me, even more possible.
Okay.
So we are here, and
so we can go to the build folder.
Yes, and we have the map.
We have the ELF file that got generated as we discussed in the build process, and a map file.
Yes.
And
so the map.
So we have not touched on map file. I guess we can start touching on it a bit. So a map file is like I like to think of it as logs of a linker. So as linker keeps working, it starts logging certain very important things into a scratchpad. And that scratchpad, I like to feel as it's the map file is a scratchpad for the linker. Where as it starts processing, it starts typing over here. So it will record what memory segments were used, what was the memory configuration. So if you look at line number 5 and 6, this is exactly what you defined in the memory command.
Right. Yes.
and
also the
then it will
attributes.
start looking at each of the sections and start recording each of the sections.
Right.
And
And
it will,
I should mention that
yes,
these are the relocatable object files that it had created, and
yes.
it is consuming those during the linking. Go ahead.
It is consuming the archives as well.
Yes. So this, for example, is the .a file, and then there has to be a .a file here, right? So
Yes.
both of them. Okay, let's go forward.
Yeah. So I guess once it is done, so the next important thing was sections, right? And this is where we talk about it. So what linker thinks is, what is the outer section and what should I keep inside it? So if you look at the dot vector, it is one space back, which highlights a directory kind of structure, right? So it says that the dot vector is the outer directory, and within it you have vectors and reset handlers, and here are the addresses for it.
Yes. So this is for vectors, this is for reset handler.
Yeah. And as we said that you will find, or when we talked about it, that these symbols, whatever we are creating over there, linker will keep track of it in a symbol table and will push them into a map file for debug. So if you look at line number 22, it shows us that the S vector is actually located at 800.
Yes.
The S vector points to this memory.
Yes. And okay, I think I'll just say something about S vector. There is a way in which you dereference them or use them.
Yes.
Actually, not dereference, but consume them in the C code, and we'll see that also.
Yeah.
Right. This is not to be thought as a variable. It is not a variable. It's
an entry of limber table. It's an entry in the symbol table.
Yes.
Okay. And if we go down, and I guess we can switch to main.c first and show them what was there in main.c. Maybe open it on the left. Move it to the left and open the map file to the right.
Okay, so I'll keep it on the left, and the map file. Where is the map file? Goes on the right. Yes. And I will maybe, let's do this. Correct. Let's go.
Let's first switch to the dot data section, because this is where we talked a lot about the initialized and non-initialized variables, right?
Yes.
So if you look at the dot data section, and if you look at main.c.o, it down. That's
main.c.o. Okay.
That's the rel.iaplt section.
Which one? Line number?
So line number 71. Come to line number 71.
Okay.
Yeah.
Yes.
So if you look at line number 72, it basically says that there are two initialized dot data variable that I am putting in the dot. There are two initialized variable in the dot data section of main.c.o, which I am picking up and putting in the dot data section in the final. And I'm assigning them the addresses 2 all zeros and 2 or 00004.
Yes.
And this is how you dereference. So let's say you are running into some exception and you suddenly found an address and it says data fault while accessing this address. The first thing you do is take that address, look into the map file, and find out the variable that address points to.
Yes. Yeah.
And similarly,
this is why people should know what a map file and what linker is and how it works. Yeah, go ahead.
Actually, there is a shortcut as well, which a lot of people don't actually use, and I will cover that later. You don't even need to open a map file or generate a map file to do all of this.
Okay. Cool.
But advanced, those are. So there is a direct utility from GNU called address to line.
Okay, yes, and you feed it the address and it
it tells you exactly which C line which line in C code it refers to.
ADDR.
That may not work on. I don't think that works on variables. That works on the instructions.
Sure. Yes, I agree.
Yeah, but that's one of the shortcut ways. But if you look at our code as well, main.c, line number 5 is not initialized.
Yes.
The variable is not initialized. And as per our discussion, this should go into the BSS section. So let's jump into the BSS section. And we can see on line number 88.
Yes.
It says that there is a variable called C that I am putting in the BSS section.
Yes.
And I am assigning the address 20008 to that BSS.
Yes.
To the variable.
Yeah.
And if you look at rest of the place, there is no other mention of any other variable because there was no variable over there.
Yeah. Yeah.
And maybe let's do an experiment as well. Why not in our code, in inside main, declare another variable, volatile int,
Oh, you want it to
to
be
just
volatile?
showcase. Let's just put it
Okay.
volatile.
So it doesn't get optimized out.
It
Fair.
won't
Okay.
optimize it. It's O0 already, but it's fine. Int z
Yeah,
is
sure.
equal to
Let's.
3000. Let's initialize it as well.
Okay. Okay. And then
And let's compile this one.
Fair. So
Our experiment is to show that this will not come into .data or .bss.
Understood. So let me just
Make.
do a make. We are, well, actually it's just unaffected. But let me close and, open the file again just to be sure that I picked the right one. Can I do a make clean here?
You can do make clean. Yes.
Okay. Let me do a make clean so that everything is wiped out. But is it?
So it won't wipe out the
files.
map file because it doesn't track the map file.
Okay, let's delete the map file. Right, just to be super sure, and then I do make, and okay, everything got generated. Cool, map file is back again. Let me put it here. Let's go.
Yeah, can you search for Z?
I think
we should not find it.
Yeah, it doesn't exist. Yeah, doesn't exist.
And that just shows the experiment, right? That's what just proves it. Anything you declare within the scope of a function is just on a stack.
Yes. Unless.
And can we look at stack as well? Is there a stack tracked over here?
I don't think it will. No, there was stack top. So if we see stack top here, so again, this goes back to how the M class CPUs boot. So we are providing this stack top, which is pointing to the end of the RAM region. So you have the flash region here, you have the RAM region here, and the stack is pointing, the stack top is pointing here, and it will start to fill backwards from here, right, during function calls. And do we want to show that as well, just briefly? It's in the startup codes.
We can show that.
Yeah, briefly, let's just show that.
So we can show that the dot vectors, which is located at 0, 0. And when we looked at the Cortex M boot process in the slides, we showed that when the ARM Cortex M boots up, it looks at the first two words in the memory and expects the first word to be the stack pointer, the location of the stack pointer, and the second one to be the is the reset handler address, which it loads into the program counter.
Correct.
So this is the minimal vector table that you should set up.
Correct. There can be other entries here. Again, other videos talk about it, but that we have skipped here. Also, at this point, let me just highlight the point that I was making earlier. Look at the fact that the stack top is actually a symbol.
Yes.
Right? It's not a variable again, it's a symbol. And that symbol gets consumed using this ampersand followed by the symbol name. And what happens is, whatever address this was holding here, right, that is the number
you will get
ABCD. Yes, so that gets put here.
Right? So in our exact case over here, you will get the address 0x20000 something.
The last address, yes.
Again, the end of the RAM.
Yes, the end of the RAM meaning. Okay, briefly showing it again. Man, the emojis are messing up with me, but
so 2002000. So origin plus length is what will be provided to the and ampersand of stack.
So this
is stack underscore.
This is, and remember we are also talking about providing again a linker keyword, talking about providing this symbol to equate to this value right here.
Yes.
Yeah.
And you can access this variable by external it. So if you look at line number 8 on the left side, you will see that we are accessing underscore stack top by external it.
Yes. So right here. Right. And can you also speak to the fact why we are making it void stack top void? Why are we calling it that?
We just want vector table to look as a
Yeah,
unified
okay.
array, and rest of the
Okay.
interrupt handlers look like a void function pointer. We can think
Yeah.
of the vector table as an array of void function pointers. And if you
Yes,
want to
which is
put
happening
stack,
here.
why not just emulate stack as that as well?
Yes.
A void function
Yes.
pointer.
So the reason I kind of brought your attention to it is all of these are also symbols which are defined elsewhere here.
Yes.
This, this, this. So all of
This.
these are also available here, right? And we are kind of saying that these are like integer numbers, and here we are treating it like a void pointer. But at the end of the day, all of these are like numbers, and that's
Yeah.
what matters. And yeah, that's about it. And we are marking it as extern so that the compilation goes through, and during the linking phase all of these are resolved.
Yeah.
Right?
Yes.
That's the idea. Okay, I think we diverged, but that's okay.
Okay.
Right, back to the
But I guess anyways we had to cover that, right?
yeah, we had to. It was just that I felt I diverged too soon. Yeah, go ahead.
So I guess the second thing I wanted to cover is how do you define multiple memory segments, right? So it's not a hard and fast rule that you define the memory segment as they look as the memory in the outside world. So what happens is sometimes people like to segregate a similar memory into two portions. For example, in real world applications, you might use Flash to store both bootloaders and application. So you want your application to be not aware of that memory. So what you do is you create multiple sections in there, and you just manipulate the memory sections according to it.
Right. So what you're essentially saying is, for example, you have separated out vectors as a section, right?
Yes.
Even though it also has some code. Reset handler, for example, would be code, and vectors. This would be that array. And then you have also separated out text where all of the other executable.
So exactly. So here what I could have done, even to if I wanted. So after stext section, instead of creating a separate dot vector output section, I could have moved line number 23 and 24 to line number 33 and 34, and it would have made absolutely no difference.
Yes. So this was pure convenience.
This is pure readability.
Readability, correct.
And the reason to do that is so whenever I at least I use it as a thumb of rule whenever I create my own section. So if you look at dot vector and dot reset handler, these are not C standard sections. These are something we are generating. So whenever there is a section that I am generating, and so whenever we do such a purpose, we actually want them to be at a very defined memory location.
Yes. Right.
And not at a very random location that and allow linker to instead of getting linker to assign their addresses, we want us to be sure that they are always located at a defined location. And whenever you want such a behavior, I usually follow a thumb of rule that I separate out the section itself, the output section itself.
Okay. And then this is how you're marking a C code with a particular section. So this is provided by GCC or GNU toolchain again, that it provides you with attribute, again, not a standard C thing. This is something that the compiler understands. And we call it compiler attributes. And what we are saying is, we are saying, hey, whatever follows the data structure or the function, data type or function, that should go into the dot vectors. So when you compile and generate the .o file, please be sure to generate this section and put this content, whatever follows here, this content, put it right here. That's the idea.
So if this dot vector would not have been there, it would have, I guess, gone to a dot data section because it's a global initialized data.
Yes.
So the compiler would have put it in a dot data section instead of putting a dot vector section.
Right. And what we wanted to do was put it at the very start. And we wanted a control over the positioning, and that's where we said, okay, let's do one thing. Let's put it in a separate section and then ourselves, put that section, man, this emoji. So put this section, god damn. Okay. So put this section as the first thing in the code memory. That's what we wanted to
Yes.
do. Yeah. Okay.
And
Let's.
and I would like to highlight the purpose of the used over here. Just like
Mhm.
we told keep to the
Hmm.
linker, that you
Hmm.
don't estimate that just because this section is not getting used,
Don't throw it
don't do
away.
it. We want
Yes.
compiler to understand the same thing as well.
Yes. So this
And
is
that's where
for
the used
GCC.
variables comes in. This is
Yes.
for
So
GCC compiler and that is for GCC LD.
yes. So where was that? Provide. Uh, what was
Keep
that? Keep.
23.
Yes. Okay.
Keep.
Yeah. This
This
is
is for
for LD.
GNU LD to understand.
Yes. Okay. And this is for GCC. Same thing here,
GCC.
by the way. So we have this function that we want to be put in the reset handlers section. This again, this section name is completely up to us. We could have called it anything. Dot Piyush is also a perfectly
Yeah.
correct section name. And again, I think I also have a video that explains how to write linker scripts and what means what, also covered there. Yeah. Go
Okay.
ahead, Rajat.
So I guess we covered almost everything.
Oh, we're done. Okay, nice. We are ahead of ourselves.
Yeah,
So
we
in the
covered
map
almost
file,
everything.
yeah, didn't even realize. Okay, so we have the .text section, which is again, I'll maybe highlight the fact that it's composed of. So this output text section, again, when I say output, it's output as marked here, right? It is composed of all the .text and .text .star sections. Again, star is a wildcard, meaning .text .abc .xyz blah blah blah. All
Yes.
of them will also be considered to go here, and we are then also taking the read-only data. Do you want to speak to what read-only data is?
So
If
read-only
you
data is all constants, right?
okay,
That
yes,
are never
correct.
gonna change.
Yes. So if there are constants, so for example, somewhere if we had const x equals to int x equals to 10, so this number will go in this region, the RO data
Yes.
region. Right. So then what we are saying is all the text section goes here. Then, the text section should be marked with start of text and end of text, e-text, start text. Similarly, we are composing the data section. And then we are also composing the BSS section, and we are saying, hey, I don't want this to be loaded. So in that final image that you make, so text section, data section, actually, okay, vectors section, text section. So this is the vectors, this is the text, this is the data, and after that there could have been a BSS. Right?
But
But
we
we
don't
say,
want it.
okay, don't even load that. But what you can do is just tell me where would you put that and where would it end, right? So just
Yes.
give me the start and the end address, and during the startup phase the reset handler can go ahead and clear all of this to 0,
Yeah.
for example. I also want to briefly talk about this syntax here. This is a funny one, right? So we are
Yeah.
saying something about RAM and ROM both, RAM and flash, sorry.
Yes.
Right? So what this I think has to do with one important insight, which is, remember that the global variables that we have here, we might want to modify them. So let's say at this point I wanted to do a equals to 10. So the question is, I should be able to modify them, and that's the key. So when we said we want the text section and the data section, right? So the value of a equals to 5, which is this, and the value of b equals to 6 was kept here, and all of that needs to go in the flash. But the thing is, the flash is like read only, right? Read and executable. If we look at it on the top here somewhere, and Rajat, you can correct me if I get any of this wrong, but we are saying it is read and execute only, this flash section. But the thing is, I'm wanting to modify it to 10. So that write must go through. So what happens is the data will be loaded here, but the addresses would be generated for the RAM. And addresses will be generated, meaning when the linker is linking all of the code together, the code that is generated as part A equals to 10 here, that code will say, okay, actually the data section lives here, right? So A equals to 5 also exists here, B equals to 6 exists here, and I should go, this line here will translate to, okay, go and modify the variable A available here. And this is the
Yes.
tricky piece. Right? So what happens now is with this line, we are saying, hey, I want you to generate addresses as if data section is in RAM, right? But actually, when you are doing, all of the merging of sections, put the data section here in the flash.
Yeah.
Right? Just so that I have these initial values. And what will happen is we'll use this, SRE locate. So S relocate and S end of relocate. These two symbols. In the startup code, what we do is we copy all of the data section from here to here. Right?
Yeah.
So all these initial values will get copied. And
Yeah.
in the code, then the A and B addresses will be generated as per this.
So
Okay,
I
I
guess
think with
so.
this.
I wanted to cover it later, uh,
Oh, okay.
for a reason.
Okay.
So the reason is I didn't want people to get confused between Flash and RAM,
Yes, but I think
and
I
why we are
managed.
yeah. So, but anyways, it's covered. So I think it makes context for me to share that as well right over here.
Okay,
So
go ahead.
why we have given the attributes of read and execute to Flash and not read, write, execute? It's not like Flash is not writable. Flash can be written. You are programming a controller, you are actually writing a
Yes.
Flash. So
Yes.
why are we giving read and executable permissions only over there?
Yes.
So the reason for this is and this is one of the reasons why people, instead of using Flash as a tag name, usually like to keep that name as ROM, so that people don't question why it is writable, why I cannot write
Okay.
to it. ROM
Yeah.
means read only memory.
Yeah. Yeah.
Yeah. So the reason it is because the way you write into Flash, right? It's not as simple as writing a variable over there. You need
Yes.
to follow a lot of steps to write into Flash, and a Flash
Yes.
is not it's
Not
byte
byte right.
writable, but it is not exactly byte writable. You can write it only once. You can write the byte only once.
Yeah.
And we will cover a lot into Flash technology where I will explain why.
Why?
So the problem is whenever you want to write a byte and you want to so think of it like this way: Flash can only set ones to zeros because of the technology, and we will understand why is it so. So Flash can
Yes.
only write 1 to 0, but the reverse is a very expensive process.
Yes. This needs to be done in, again, bulk. Just a teaser.
Yes. So when you want it to go from 0 to 1, the only way is you erase a complete block.
Yes.
And in which the data is gone. So you need to do a lot of buffering, modify, erase, and write to modify a variable twice. And that's a very expensive process. That's a very time consuming process.
Correct.
And that's why, but you need to do dot data variables. The global variables, you need to modify them on a very consecutive basis. That's why we don't want dot data section to actually sit over there.
Yeah.
Because if we want to change the value of the variable, we need to do a lot of processing to change the value. So we put it into a memory that is easy to write, which is your RAM.
Yes.
So that's why, but why do we want it to sit on Flash? The point is Flash is non-volatile memory.
Yes.
While, Flash is a non-volatile memory while RAM is a volatile memory. Yes. I always get confused while speaking.
Yeah, understandable. Yes.
Slip of tongue happens. So,
yes.
So what happens is, but I know I need this dot data variable when I want to start next. Else my program will not start correctly.
Correct. So let me just speak to it a little bit so that we're on the same page. So this is the Flash. Okay, this dot is not required. Flash, and this is the RAM, and this is part of your controller, and somewhere there is a CPU, and there is a power switch here. So what Rajat is mentioning is if you power off this controller, this data will still stay intact because this is something like your SD card or USB pen drive or USB drive kind of a thing. So this is retained, but this is lost.
Yes.
Right. And this is like, hence RAM, read-only memory and volatile. This is non-volatile.
Random access memory and
yeah. Oh, sorry. Slip of tongue. Random access.
So now you see, right now this is where the problem comes in. We want that data variable to be available to us during boot up, but we also want it to be fastly writable.
Yes.
So now we end up in a situation where we want this data section to be available at two places.
Yes.
While boot time, we want it to be available at flash, so that it is retained during power
the
cycles.
Initial values. Yes.
But on runtime, so that we can fastly modify them, we want this data section to be in RAM, so that our code modifies only the values in the RAM.
Yes.
Hence, you have to write that weird syntax of RAM at flash, which basically says that you can generate the binary as if it is as if this will be stored in data section, but to the rest of the code, make it look like that these addresses are actually in RAM. Yes. So that when they are accessing, they don't access the flash, they access the RAM itself.
Yes. Yeah. That hopefully, if people watch this piece back and forth again and again, it will make sense. If it doesn't, I think, the next session that we'll have, which is boot to main. How does
reset
the CPU boot?
Yes.
Reset to main. How does the CPU go from booting up to landing in the main function? And again, why main is not the only function it can land at. So all those things, again, we'll reiterate, and I think it will be a lot more clearer there.
Yes.
Okay, cool. I think then with this, we're pretty much done with what we wanted to cover today.
Yes. Yes.
All right, perfect. So I'll go ahead and stop the recording. And for those
and
of
pray
our
that
audience,
it is recording.
and pray that it is recording. And those of you who stayed back this long, thank you for hanging around. It's because of people like you that we want to give out more and more, and essentially peel all of the onion that embedded systems is. Right.
Yes.
So thank you for hanging around, and catch you guys next time. Bye-bye.
Yep. Bye-bye.